if conservation of energy is violated, then your all this law cannot be correct. So if multiplication of thrust is not consistent with the conservation of energy, then Pascal's law is not true. So you have to check that in this entire procedure of multiplying force, energy conservation is not hampered anywhere. If it is hampered, then it is not possible. What is your opinion? Is conservation of energy obeying this? That by applying a very small force you can get a very large force in this setup? See, I consider that gravitational force, gravitational potential energy change will be very negligible, because this pipe and all this setup, in this the liquid height is very small compared to the radius of the earth. So I can already consider that gravitational potential energy on both sides will remain same. But what about the energy supplied by the force applied by you and the supplied by the other force F2? That force is doing mechanical work, so it is supplying some energy to the system. So whether these are obeying conservation of energy or not, check. In from Pascal's law, can I write F1 by F2 that is equal to A1 by A2? From Pascal's law, first step, I write F1 by F2 equal to A1 by A2. Now this one is the incompressibility. Since it is incompressible, I can write A1 by A2 is actually x2 by, substitute it in this format. It is giving F1 by F2 equal to x2 by x1. Because A1 by A2 is x2 by x1, so we substitute it in place of A1 by A2. So it is coming F1 by F2 equal to x2 by x1. Then cross multiply both sides. You will get F1 x1 equal to F2 x2. What is F1? Force applied on the first piston, and x1 means displacement of the first piston. So it is the work done on the first piston. F2 is the force on the displacement of the second piston. So work done on first piston and work done on second piston are equal. So work done by force F1 and work done by force F2 are equal. That proves the conservation of energy. Work done means here energy. So both forces are producing same amount of work done, means they are obeying conservation of energy. So Pascal's law is valid, and this multiplication of thrust is also valid. Because high force, displacement is small. Low force, displacement is large. So that's why product will remain same. That is work done. Thus it is obeying the conservation of energy. So multiplication of thrust is a direct consequence of the conservation of energy. So it is a correct law. Okay. See, now we will introduce another case. Suppose a solid body is immersed in a fluid. Okay. Then it will displace some amount of the fluid to occupy certain volume. So if it will displace certain amount of fluid, then this displaced fluid's weight of the displaced fluid will apply a force on this solid body in the opposite upward direction to move this body out of this fluid. Okay, that particular force is called the buoyant force or upthrust. So there is a liquid in a container. I want to put a solid body inside the liquid. Then if I push it inside, or if I drop the body inside the solid liquid, then liquid or the fluid will try to move it out, try to throw it out. Why? Because the solid object is occupying some volume inside the liquid or the fluid, then it will displace some amount of fluid, and displaced fluid has some weight. This weight is creating a force of equal magnitude in the upward direction to move out this solid object. This particular force is called the buoyant force or upthrust. Okay. Now, upthrust of the body is acting in the upward direction, and weight of the solid body is acting in the downward direction. So, are they action and reaction? No, because they are acting on the same object. And don't even think that if the body is floating and weight of the body and upthrust are equal, still they are not action and reaction, because action and reaction cannot cancel each other. Okay, so these are completely two different forces given by two different agents. Weight is given by earth attraction, buoyant force is given by the fluid on that solid. Now, I will ask you about a certain situation. Suppose there is this kind of a box. It is half filled with water and remaining half is filled with air. Half filled with water and remaining half is filled with air. Okay, very small air is there, this much. Now consider a solid cork, a solid cylinder, cylindrical cork is floating. A solid cylindrical cork is floating in this. It is half immersed in water and remaining half is in air. Exactly half portion of this cylinder is immersed in water and other half is in air, and it is floating completely, means it is at rest. Now you are preparing a pinhole and using a suction pump, all the airs are evacuated from this chamber. Only air, not the water. Only water, air is evacuated from the chamber by using a suction pump. What will happen to the immersed level of the cork? Will it immerse more in the water? Will it immerse less in the water, or will it immerse same as before? Means half volume is immersed, more volume is immersed, or less volume is immersed. If the entire air is taken out, and it is considered that air has very negligible pressure when it is inside. Air pressure inside you can neglect. Three possibilities. Will the volume of the cylinder, initially how much volume is immersed? V by 2. If I consider volume of the cylindrical cork is V, then V by 2 is immersed initially. Then when you evacuate with all the air from this, what will happen to the immersed volume? Will it be equal to V by 2? Will it be less than V by 2? Or will it be greater than V by 2? And it is given that air pressure on the cork when the air is inside, that is negligible. What? Remain same. Then you can say that air is not a fluid. Air is a fluid. Air is fluid. So air can also exert buoyant force as well as water. So when air is evacuated, buoyant force of air is missing. See? No. Air pressure is negligible, it is mentioned. Only the buoyancy of air has to be taken into account. It will immerse more in water. How? See, previously when air and water both are there, it is floating, means it is at rest. So how many materials are applying upthrust on this? Water will apply as well as air will apply. So buoyant force of air plus buoyant force of water, that is equal to weight of the solid cylinder. Means floating body is always weightless, net force 0. So upward direction there are two forces. One is BA, another is BW. And downward direction there is weight. Okay. Now all the air is evacuated. So which force is there only? Given by water. So write it as BW prime. BW prime now in the second case. How much, what weight of the cylindrical cork will remain same? That is not affected. So now tell me, if air is so equate these two, then you will get BA plus BW, that is equal to BW prime. Then can I write BW prime minus BW, that is equal to buoyant force of air. Now Tell me whether buoyant force of air is positive or buoyant force of air is negative. All the buoyant force are in the opposite direction, so it should have a positive value. So which one is greater? So BW prime should be equal to, they should be greater than BW, because previously air and water both are applying buoyant force to balance this weight. Now only water is exerting buoyant force to balance this weight, so buoyant force of water should be increased now, because it will balance the entire weight alone. Buoyant force of air is not there to help. So BW prime is now greater than BW. Can I write? This one is volume immersed, volume of the cork immersed into density of water into G. Volume of the immersed portion into density of water into G. So more volume will be immersed now, because if it is immersed more, then only volume immersed will be more, then only buoyant force of water will increase to balance that W alone. Previously, buoyant force of air and buoyant force of water together balances W. Now air is evacuated, so buoyant force of water has to be increased to balance W. And when buoyant force increases, if the object immersed, more, so it will immerse more volume will be inside. Okay. Okay, for today, enough for today. So we will discuss in tomorrow's class, remaining part. So we are discussing about the fluid mechanics portion. We have discussed up to the concept of the buoyant force and how it is calculated, because if you consider water or any other fluid in some container and an object is immersed here like this, means the total volume of the object is not immersed inside the fluid, a part of the volume is immersed. In that case, the buoyant force that is acting on the object in the upward direction and mg is the force acting in the downward direction. Now how to calculate the buoyant force? It is the volume weight of the fluid displaced by the solid object. Suppose the V volume of the solid is inside the fluid. It is not the total volume. In this setup, it is the volume that is immersed in the liquid or fluid is the V. So we consider V is the volume of the immersed portion of the solid inside the fluid. Then how much fluid will be displaced? By the same volume, fluid will be displaced by this solid. Okay. Now we can consider this is the volume of the fluid displaced by this body. Then if you multiply with the density of the fluid, say sigma, density of the fluid is considered as sigma, then V into sigma will give you the mass of the displaced fluid, volume into density, that is mass. Mass of what? Not this mass. It is the mass of the fluid that is displaced by the body. Now, if I multiply this mass with G, then we will get the force, that is the weight of the displaced fluid. Weight of the displaced fluid. which is considered as the buoyant force. Okay. Which is considered as the buoyant force. Suppose a body is partially immersed in a fluid, then suppose the displaced fluid has a volume V. That means the volume of the immersed portion of the solid. Solid has greater volume, maybe the greater volume. So a part of the solid is immersed. That part of the solid has a volume V. Then the fluid displaced by this solid will be of volume V. Then to find the mass of that displaced fluid, we have to multiply this displaced fluid's volume with the density of the fluid. That is considered as sigma. So V sigma give you the mass of the displaced fluid by this body. Then multiply this quantity with G. Then you will get the weight of the displaced fluid. And this weight of the displaced fluid is producing the buoyant force. That is also called the upthrust. It may happen that entire object is immersed. In that case, volume of the immersed body, volume of the body is equal to the volume of the fluid displaced by the body. If the body is completely immersed. But if it is not completely immersed, then volume of the body will be bigger and volume of the immersed portion will be smaller. Okay. Now here we consider it is partially immersed. It can be fully immersed. In that case, this volume will increase and buoyant force will increase. So as the immersed portion of the solid inside a fluid will increase, buoyant force given by the fluid will also increase. Suppose it's 1/4 is immersed, then it is 1/3 is immersed, then 2/3 is immersed. So in that cases, the buoyant force will increase. If it is only immersed, then buoyant force will be maximum. Clear? Now, I will ask you one question. That is, in which direction this mg acts? Downward. Why downward? Because m is a scalar and g is a vector. G is a vector quantity, acceleration due to gravity, and its direction is downward towards the center of the earth. So I can write this one to show that this force is in the downward direction. Now, for the buoyant force, V is a scalar, sigma, the density of the fluid, that is also a G is a. So what will be its direction? So I will write G in the downward, B in the downward direction, B in the downward direction. So I will not, you should not call it up thrust, you should call it down thrust. It is the weight of the displaced fluid. So displaced fluid weight will be also due to the gravity, and that is pulling it towards the center. That should be in the downward direction. So why you consider the buoyant force in the upward direction? You are considering buoyant force in the upward direction and call it up thrust, but it is showing that weight of the displaced fluid is directed towards the center of the earth. So it should be in downward direction, isn't it? Okay, fine. Think about this question. You have one day time. Tomorrow you will tell me why this is not downward, why it is upward. Now, so how many forces in this situation are acting on this body? In general, two forces. One is weight, another is upward force, that is buoyancy. Now we consider if the body is totally immersed. consider this situation if the body is totally immersed. Then I can consider that this V is the volume of the solid object itself, and this is also equal to the volume of the displaced fluid, because I consider entire body is immersed now. See, we also consider that the density of the solid is rho. Density of the solid is rho. Density of the fluid sigma, density of the solid rho. Mass of the solid we can already write m, so I can also write m equal to V into rho. This is the mass of the solid. M equal to V into rho. Okay. Now, what happens if this downward force mg minus P is positive? Mg is greater than V. What will happen to the body? Body will go down, means it will sink. It will sink. So we can consider that in this case it will be mg prime, that is resultant force in the downward direction, that is equal to mass into acceleration. Here acceleration is taken as g prime, and this quantity is called the apparent weight. Apparent weight of the body. See, there is a decrease in the weight actually. That's why apparent weight is calculated, because mg is the force responsible for weight. Now P is in the upward direction, so mg minus B is the apparent weight of the body. So that is defined by Archimedes principle. Whenever a solid is partially or completely immersed in a fluid, there is a loss in weight, and that is called the Archimedes principle. So that's why any immersed object feels less weight. Similar to the situation of the man inside the elevator, mg minus ma. For that ma part, normal reaction will decrease, and we feel that our body is less weight when elevator is going down with acceleration. The same situation almost, mg minus v is there, that is equal to mass into effective gravity, that is g prime. So that is that's why we can consider that the apparent weight is less than the true weight when the body is immersed in some fluid. Now, first case we consider, that is mg is greater than v, so g prime should be greater than 0, and the body is going down. G prime is the acceleration here for Newton's second law. So it is going downward, means it is sinking. The body will sink. Next condition is that if mg is less than v, means v is larger, what will happen? G prime will be less than 0. G prime will be less than 0. What will happen? The body will float. Body will float. Because in this situation, suppose we have a plastic ball, and you take this plastic ball at a depth inside water and then release. What will happen? Plastic ball will move up. Because plastic ball, on the plastic ball there is a force equal to its weight. One is buoyancy, and buoyant force is more than the weight. In that case, it is accelerating upward and it will come to the top of water. So this is the condition for floating. Float at top surface of water or any liquid. Now consider the third situation. What will happen if mg is just equal to v? whenever it will float on the surface, the same situation occurs. mg equal to b. In that case, apparent weight will be 0. So for any floating object, if it floats, then apparent weight will be 0. Floating object is weightless, means mg and b balances each other. Now see the situation when the plastic ball is coming out. Then as it is coming out, volume of the immersed portion will decrease, so buoyant force will decrease as it is coming out of the liquid. Then a little bit of buoyant force will be there because to balance the weight. That's why it will float at the top surface. Now this is the situation, mg equal to b. That means net force on the body is 0 and body can float anywhere, not only at the top. Inside the liquid at any portion you can place the body and it will stay at that point. Because net force on that body is 0, so there will be no acceleration and it cannot move. Okay, now come to a situation using these two particular cases. From this, can I write that mg prime, this is equal to mg minus b is m by rho into sigma into g. See, d means volume into sigma into g. Here I consider entire body is immersed, so I consider volume of the displaced liquid is equal to volume of this solid object. What is the mass of the solid object? M. Density of the solid object? Rho. So its volume will be m by rho. So that I substitute here. In place of b, I substitute m by rho into sigma into g, because m by rho is the volume of the solid object. It is completely immersed, so volume of the liquid displaced will be equal to volume of the solid. Then this is the volume of the liquid displaced, multiply with density of liquid, you will get the mass of the displaced liquid. Then multiply by g, you will get the buoyant force. Okay, now I can cancel m from both sides, and g prime can be written as g common 1 minus sigma by rho. Now check this situation. First situation, when it is sinking, g prime is greater than 0, means rho will be greater than sigma, so that's why the body will sink. Rho greater than sigma means density of the solid is greater than the density of the liquid, so the body will sink. Next one, rho less than sigma means density of the solid is less than the density of the liquid, so it will float at the top. Now what will happen to this case when g prime is 0? Density of the solid and density of the liquids are equal, that is rho equal to sigma, rho equal to sigma. Now what do you mean by rho equal to sigma? What is rho? Density of solid. What is sigma? Liquid. How can these two be equal? If I consider a ship is floating in water, density ship is made up of iron. Density of the iron, the density of the iron and density of the sea water are equal. Then how it can float? Then this rho should not be the density of the solid material. Then what? Suppose I consider the volume of a ship, does it mean that entire volume is compact with the iron? Then where the people will stay inside the ship? If it is a solid iron block, then where the people will stay? So there are many vacant rooms, there are certain gas chambers, there are certain large areas involved which does not have iron. It is not the solid structure, it's more. Too much portion is hollow inside. So volume is large, but the mass is not that much of large. I can consider that suppose there are two spheres. One is hollow sphere, another is solid sphere. Okay, identical in volume. So both have same volume. So both can displace same amount of fluid. So when immersed, both will have the same buoyancy when they are immersed completely. But think, mass of the solid sphere is larger than the mass of the hollow sphere. So that's why this rho is not the density of the material with which the solid is made. It is the average density of the entire solid structure that is given to you for immersion. Clear? It may happen if you take only density of iron, say for hollow sphere, for solid sphere, density of iron will remain same. But hollow sphere, if you calculate the average density, that is mass per unit volume, that is very low for the hollow sphere. So that's why this type of a hollow sphere, hollow shape, like ship, can float on the surface of water. That does not mean iron has the density less than water or equal to 1. It is the entire structure of the ship produces an average density which is less than or the density of water or equal to the density of water. Means there are iron used for ship making. There are some gas chambers. In gas chamber there is air. Density of iron is more than water, but density of air less than water. So overall average density is coming less than water. That's why it can float. So write down this rho used here. The rho used here is not the density of the material, by which the solid is made, It is the average density of the entire solid structure. It is the average density of the entire solid structure. Okay. So you can calculate the buoyant force using this formula P sigma G if all these quantities are given. So write down one problem. A cube of calcium oxide, having volume 10 centimeter cube, is completely immersed in water having density 1 gram per cc, considering G equal to 980 centimeter per second square, means all in CGS unit. Considering small g equal to 980 centimeter per second square, calculate the buoyant force on the cube. Calculate the buoyant force on the cube. But earlier we have the formula of buoyant force, that is E into sigma into G. V is the volume of the displaced fluid, sigma is the density of the fluid, and G. So volume is given, sigma is given, sigma is for water, volume is already given, G is given. So what is the answer? All are in CGS unit. What is coming? 9,800 time 9,800 time. In CGS unit, force is measured in time. Unit is time. TYNE. All of you calculate. What is coming? 9800 time. So is this problem very tough? No, very easy. Just multiplication. All of you have completed class 12. So no multiplication is given to you. Check the problem. This multiplication can be done by a class 8 student. He will multiply these things and say this answer. You are in class 12, completing class 12, so no normal multiplication is given to you. Just check the question. It is not the correct answer. I deliberately write this formula once again because then you will try to apply this formula, don't even thinking the other conditions. See what is given. The cube is prepared with calcium. It will react with water. So you cannot calculate the buoyant force. The solid that is to be immersed in water, for calculating the buoyant force or validity of Archimedes principle, it should be non-reactive. You forget the conditions of Archimedes principle. So if this type of question is there should be 3 options and 4th option will be none of this, and that is the correct answer. Okay. So for all this validity of Archimedes principle, you have to consider that the solid that is immersed in the fluid should be non-reacting. It should not chemically react, or it should not dissolve. Suppose sugar cube is given and it is immersed into water. Not possible because it will start to dissolve. Okay, so write down for the validity of Archimedes principle. For the validity of Archimedes principle, the solid that is immersed in the fluid, that is immersed in the fluid, Number 1, should not dissolve in the fluid. Should not dissolve in the fluid. Should not number 2, should not chemically react with the fluid. Should not chemically react with the fluid, because in these conditions Archimedes principles are not valid. Principle is not valid and you cannot calculate. Oh, the number 1, it should not dissolve, solid should not dissolve in the fluid. Number 2, solid should not chemically react with the fluid. These two are strictly prohibited. Then you can only apply Archimedes principle to calculate the buoyant force and all these things, the apparent weight. Clear? Pressure at a certain depth depends only on H rho g. HdG or H rho g means at the bottom it will produce same pressure in each container, though the amount of fluid in the container will be different. Force will be different at the bottom of each container, but the pressure will remain same. Area difference in area does not matter, because inside a fluid pressure at a certain depth does not depend on the area. HdG, it does not depend on area. So pressure at the bottom of each container is same if only density of the liquid is same. Here I mentioned the same liquid, water, and height of the liquid in each container will be same. So pressure will be same. This is called the hydrostatic paradox. It appears that if the mass is different, area is different, then pressure should be different, but it is not different. Hydrostatic paradox. Okay? Now we will discuss other part of this topic, that is the fluid mechanics portion. First we have to discuss two types of flow of fluid. One is called the streamline flow, another is called the turbulent flow. Streamline flow and turbulent flow. What does they mean and all these things that we'll discuss. And before that, I want to discuss a very small concept over viscosity. Viscosity, what viscosity is? Viscosity is actually a friction which is acting between fluid surface or between fluid solid surface. Whenever the fluid is involved in the and relative motion of the fluid occurs with respect to some solid surface or with respect to some fluid or between the two layers of the fluid, a friction force will be there to stop this motion. It will try to retard this motion. That force is called viscous force, or phenomena is called viscosity. It is similar to friction, but not the friction between solid object that we have discussed. Now, Let us consider water is flowing in a river, and then divide each layer of a water as a lamina like this. So this is the first lamina. The next to it there is another lamina. There is one other lamina. All this. So this is generally termed as the laminar flow. Means we are considering water is flowing in a river, and this is one layer of water, this is another, then another, then another, then another, up to the river bed. Now tell me, at the top, the first lamina of water, it is in contact with the air. At the bottom, it is in contact with the river bed, that is solid. Then which lamina will feel maximum friction? Obviously the lamina at the bottom, because it is in contact with solid surface. So solid liquid friction is greater than solid liquid air friction, because top surface is liquid air friction. Now in between this, the layers are feeling a friction that is due to liquid. So that is also midway between this solid liquid maximum, liquid medium, then liquid air more exactly minimum. Okay. Now then which layer is returning maximum? The bottom layer. And which layer is more faster? It is faster. First, as you are going upward, you will getting faster and faster lamina. They are moving faster. Okay. So now let us consider any such layer. Suppose this layer has a velocity v in this direction. Then you move above, and you will find that as you are moving above, you are getting more and more lamina having more velocity, because as you are moving up, viscosity will decrease, and as a result you will find the faster layers. So here, suppose after moving a certain distance Tx, you will find a layer which has a velocity v plus dv. So in one layer you find velocity v, you are moving up, means you are getting the faster moving layers whose velocity are increasing. Then by moving a distance dx, you will find another layer whose velocity is v plus dv, slightly more than v. Then we can consider that dv by dx, this term as velocity gradient. Like when you are performing derivative dy dx, that is called gradient of y with respect to x. This is the gradient of the curve dy dx, or slope of the curve. Similarly, this is the velocity, derivative of velocity with respect to position dv dx. So rate of change of velocity with respect to distance moved. So that's why it is termed as velocity gradient. Okay. Now consider area of each lamina is capital A. Then why the next one by one laminas are moving slowly? Why their speed decreases? Because of this friction, that is called viscosity. So viscous force will be acting tangentially on any lamina in this direction. If this viscous force is acting tangentially on any lamina in this direction, Clear? Then we can write that it is calculated experimentally that F is proportional to area of each lamina in contact. Because we consider the laminas are in contact and each lamina is of area A, then this viscosity is proportional, force is proportional to area of lamina. And it is also directly proportional to the velocity gradient. Means as the velocity is more, the friction will be more. Velocity increases means friction will also increase. So that's why we consider that viscous force increases with friction. It increases with velocity. Viscous force increases with velocity. So that's why in the pendulum experiment, to cancel the viscous force of air, we consider a very small angle such that velocity of oscillation will be very small and we can neglect the viscosity of air. Then from this we can write F equal to some constant. Constant is denoted by eta A dV dx. This is the form of the viscous force. Eta A dV dx. From this we can define the this eta is called the coefficient of viscosity. It is similar to the coefficient of friction that we have discussed. Same property, because eta increases means that fluid have more viscosity. Like if mu increases, the surface is more rough. We can say that eta increases means the medium is more viscous. Okay. Now, in general, for a solid object, suppose a spherical object, solid sphere or any spherical object, it may be hollow but still spherical object. If it is falling through a medium, it is falling through media, then in that case, if this solid has a radius r, then viscous force on this solid object can be written as F equal to 6 pi eta R V suffix T. 6 pi eta R V. This law is called the Stokes law. Stokes law for calculation of the viscous force on a spherical object. Viscous force on a spherical object. Except 6 pi, you can find the other quantities present in the formula by using dimensional analysis. That F is depending on eta, F is depending on radius and F is depending on velocity. Then you can determine that F proportional to eta, F proportional to R and F proportional to Vt. And 6 pi, this constant cannot be determined by dimensional analysis. You have to find it experimentally. So it is already found that this one is the viscous force. I write only the magnitude because this friction can, in the problem, you can write with the according direction by putting plus or minus. Now, what do we mean by Vt? Why not only V? This velocity is constant. That is called the terminal velocity. Let us consider a situation. Suppose a spherical raindrop is forming and it is falling from the cloud. Okay. Now This spherical raindrop, when formed from the cloud, suppose, it is moving down through which medium? Air medium. Now we consider that air has a constant density, atmosphere has a constant density. Now, what is the net force acting when it is just formed? What is the net force acting in the downward direction? It is falling towards the earth. So one force is pulling it towards earth. What is that force? H. Okay, fine. So I will draw it little bigger. Then one force acting on this, that is H. Fine. But it is inside air medium, so it will displace some amount of air, and that is producing a buoyant force, and that buoyant force will be in the upward direction. So buoyant force will be in the upward direction, that is B. So with which force it is falling down? mg minus b. mg minus b is the resultant force in the downward direction due to which it is falling. Now see, since it is falling down with a resultant force, it will accelerate. Acceleration means its velocity will increase. Velocity increases means viscous force will also increase. And viscous force is acting in which direction? That is also in upward direction. I write it by small f. Since it's like friction, I write it small f. So this viscous force, as given by Stokes' law, is acting in the upward direction. Now tell me, the velocity is not constant. It is increasing because of the acceleration, and as a result viscous force will also start to increase. So one time will come when the viscous force is increased that much that viscous force plus buoyancy will be equal to mg. Then what will be the net force? 0. One time will come when the increased value of viscous force added with buoyant force and balances mg. Then net force on the raindrop will be 0. Then what will happen to the raindrop? It is falling. But one time will come, its velocity of this raindrop will become 0. Then what will happen to the raindrop? What will happen to the raindrop when net force is 0? What will happen to the velocity of the raindrop when net force will be 0? Will the velocity be 0? No. Because in that case you will find that rain is falling and suddenly start. It is not possible. The large velocity it has just before the force to be 0, with that velocity it will continue to move remaining part, and that is a constant velocity. Because once the net force is 0, velocity becomes constant, and once velocity is constant, viscous force cannot change further. Because if velocity changes, then only viscous force change. Velocity increases means viscous force will increase. But when the net force is 0, acceleration becomes 0, and viscous force and the velocity remain in the remaining part. So viscous force will not change, and the entire motion in the remaining part will be a motion with constant velocity. Okay, that constant velocity achieved at the terminal end is called the terminal velocity. So that is used in Stokes' law. This is not the instantaneous velocity when it is changing. It is the terminal velocity. So that's why I use the term T. You cannot use this formula directly when the velocity is changing. You can only apply once the body achieved terminal velocity. Okay, then initially when it started from the cloud, its velocity is 0. Now what will be the graph between velocity and time? Like this. Initially the velocity is increasing because of the acceleration, but now viscous force is also increasing, and one time will come when viscous force is increased that much that viscous force for buoyancy, buoyant force will be equal to mg, and net force will be 0, and acceleration stops to 0. Acceleration comes to 0. The body moves with constant velocity. So that's why now the velocity becomes constant. This particular velocity is termed as dt, terminal velocity. So initially acceleration is more. Now as the time goes, as the body moves, the acceleration is decreasing, and one time will come, acceleration becomes 0. Okay. Now, if some equation is given to predict this terminal velocity, I will write the empirical form. Entire form you can solve by solving the differential equation, but we will not go into that detail. This velocity at any moment can be written like this: some constant mg by k into 1 minus e to the power minus k by m into t. This type of a format will come for the instantaneous velocity when the raindrop is falling. Instantaneous velocity at any moment. Okay, this type of equation will come where k is a constant which contains this viscous coefficient, buoyancy, all these terms. Viscous coefficient is contained in k. And this is a combination of the constant that I considered as k. Now check, after a very long time this terminal velocity is reached, and that is a constant value, and this velocity is the instantaneous velocity because it depends on time. At each and every time the velocity is changing. Now if you put t tends to infinity, what will happen to this term? E to the power minus infinity means 1 by e to the power infinity. E to the power infinity is infinity. So 1 by infinity means 0. So this term will vanish and it will be just mg by k. That is a constant value. That is termed as the terminal velocity. So if this equation is given and identify the graph, then this graph will be there. So initially when you put t equal to 0, this function will be 0. This point, then it is increasing, and when t tends to infinity, it will be a horizontal line. So this is the growth. In the same graph that you find in case of growth of a charge in a capacitor. Same graph will come. Growth of a charge in a capacitor. Okay. Now, and for this particular case, for spherical body, we can calculate the expression for the terminal velocity. That is, see, when the terminal velocity is reached, I can write that b plus f, that should be equal to mg. b plus f, that is equal to mg when terminal velocity is reached. Clear? Then what is B? V into sigma into G, where sigma is considered here the density of the air through which the raindrop is falling. So this B can be written as 4 by 3 pi r cube into sigma into G, because volume of the raindrop of radius r, it is a spherical, so it is 4/3 pi r cube into sigma into G. This is the buoyant force on the raindrop. Then viscous force, we can calculate it from Stokes law. Directly put from the result of the Stokes law, that is 6 pi eta r Vt. Now this is mg. mg is the weight of the spherical water drop. So it has a volume 4/3 pi r cube. Density of water is considered as sigma rho into G. I consider the density of the water as rho and density of the air as sigma. Okay. So that is m is volume into density into G. Then we can write 6 pi eta r Vt, that is equal to 4/3 pi r cube G into rho minus sigma. 4/3 pi r cube G into rho minus sigma. Then many things will cancel. Pi cancel, 3, it will become 2. So from this we can write Vt equal to 2 by 9 eta r square G into rho minus sigma. Vt equal to 2 r square by 9 eta into G into rho minus sigma. That is the expression for terminal velocity of a spherical drop object in a medium. So if certain problem will come, you can remember this formula and directly put. Streamline flow and turbulent. Streamline flow means this is drawn like this. Suppose this is a pipe which this is considered as a pipe and through which liquid is flowing. So I can consider certain line inside like this. Tangent drawn at every point to this line will determine the velocity of the direction of velocity of the fluid at that point. If I draw any tangent at any point to this line, that will determine the direction of velocity of the fluid at that point. Clear? These lines are called the streamlines. There is no such line in the fluid flow. We just imagine this one. This is the imaginary lines. Okay. And how these imaginary lines are considered? If I draw a tangent at any point on this imaginary line, then it will show the direction of velocity of the fluid at that point. Okay. Then I consider such points. One is A, where a tangent is drawn. One point B, where is this tangent drawn. At this point, there are this tangent. Point A, point B, point C. At this point, speed of it is dA. It is given dV. Direction is given by the tangent. And this is BC. You can draw other tangents on other streamline. I draw on single streamline. This one. Now, we say that a particle of the fluid having velocity VA, a particle of the velocity having value VA, a particle having velocity VA. And when I tell you this velocity is VA, you immediately say, oh, it is at point A. When I say that this particle has different velocity, say VB, you will immediately say that the particle is at VB. Which particle is at A, that does not matter. Whatever be the particle that comes to A must have the velocity VA. It may come at 10 o'clock in the morning, it may come at 11 o'clock in the morning, it may come at 2 p.m. at noon. Whenever the particle comes to A, it should have a velocity VA. Then the position of the fluid particle in this motion is characterized by its velocity. Position is characterized by velocity. Generally, we characterize velocity by position and time. Here, position is characterized by velocity. This type of motion is called streamline motion. Means at each point, the velocity's magnitude and direction will remain same. At each point. So, at t equal to 1 second, if it has certain velocity in certain magnitude and certain direction, then at t equal to 10 seconds, a different particle will come, because water is flowing, a different particle will come to this point, but it should have the same velocities, magnitude and same direction if it comes to point A. So all particles at different instant of time, when they come to point A, they should have the same velocity VA, both in magnitude and direction. Then this particular motion is called streamline. Clear? So write down. Draw this diagram and write down. Streamline motion means at each point on a streamline, position of the fluid particle is characterized by its velocity vector. It is like that. Position of the particle is characterized by its velocity vector. It is like that if it is said that, okay, the velocity of a boy, of a student from you, velocity of a student is 10 meter per second towards the north direction. If it is given, I will consider that student near the SIRT written structure where you perform the yoga today. That front gate, SIRT structure. The velocity is given and direction is given, and immediately I say, which student, that does not matter. Velocity given, direction given. I said that the student, where is the student? I said that it is near the SIRT written. So that's why velocity is characterized by this. Suppose velocity is given 5 meter per second. I will say near this classroom. Outside, just outside this classroom. Know which student, that does not matter. This velocity means this position should be this one. Whatever student it can be there or not, it should have velocity there. It may be x, y, z or any one student. But if its velocity is specified, I will immediately specify the position as this one. So each position is characterized by its velocity in a straight line motion. Okay. But in turbulent motion you cannot do so. Why? Turbulency means some kind of rotation. And if there is a rotation, at each point the direction of velocity will change. So in turbulent motion, right now, in turbulent motion, position cannot be characterized by velocity only. Position cannot be characterized by velocity only, because with time velocity's direction will change at the same position, because with time velocity's direction will change at the same position. Now this method will not work. With time, velocity vector's direction will change at each position. Because it is rotating, turbulency means some vortex and eddies will form and it will rotate. Vortex will form and it will rotate. So it will changing the direction always. At each point, the direction is also changing. So now you cannot characterize the point by giving its magnitude of velocity and direction of velocity, because direction at the same point is changing. Okay. Now, these are the differences. Mostly we will whenever we will discuss anything, we will not discuss turbulent motion because that is beyond our scope. We will consider only the motion as if it's a streamline motion. Now, first one is that we consider a pipe like this. Like this. And we consider a liquid is flowing like this. Which type of liquid or which type of fluid? It should be Newtonian fluid. What do we mean by Newtonian fluid? The viscosity is very small. If it is a non-Newtonian fluid, the viscosity is too large. So for that, this calculation and all these things will not work this way. So those are more complicated. And even for highly viscous medium, Newton's third law is not obeyed by that viscous force. If it is highly viscous, we consider only the viscous force directly proportional to velocity in Stokes' law. But there are mediums where viscous force is proportional to velocity square or even more, higher power. In that case, for highly viscous medium, all these calculations will not work, and that's why we consider only Newtonian fluid. Newtonian fluid means very low viscosity. And the entire motion of the liquid or fluid through this pipe is considered as streamlined. We will never consider turbulent motion because that calculation is too much complex, and that is beyond the scope of even for JEE. Now, we consider that a liquid is flowing through this one continuously. I consider a liquid column. We consider when the liquid is going into this pipe at this end, it has a velocity v1. So in a certain time delta t, how much this liquid layer will move? I consider this much. That is E1 into delta t. So in time delta t, this liquid layer moves forward by an amount V1 into delta t. V1 delta t. This much. Now, there is some area of cross section. That area of cross section is taken as A1. Okay. So, how much volume of the fluid in time delta t enters the pipe? A1 V1 delta t. So, that is the volume of the fluid that enters the pipe in time delta t. Then, right? Volume of the fluid enters the pipe in time delta t. Volume of the fluid enters the pipe in time delta t is A1 V1 delta t. Okay. Then we consider that through this end, the water is coming out of this pipe, and we consider at this end the velocity is V2. Velocity is V2. Okay. Then I consider area of cross section of this end is A2, and consider that the liquid near this fluid near this end, consider a distance V2 delta t in time delta t. Since the velocity near this end is considered to be V2, then V2 delta t is the distance traveled by the fluid in time delta t. Then, how much volume of the fluid will come out in time delta t from this end? A2 V2 delta t. A2 V2 delta t. This much volume of the fluid should come out from the pipe in time delta t. Now, will these two volumes be equal or unequal? This should be equal. Why? Because first of all, when we consider this, we consider the incompressible fluid. That means the volume of the fluid that enters the pipe in a certain time will be equal to volume of the fluid that leaves the pipe during the same time, because the volume inside the pipe will be fixed. It should not be changed. But provided for that there should not be any leakage through which liquid, fluid or liquid can come out, or fluid or liquid can be injected in between. Okay, now then we can equate this. Then cancelling delta T, I can write A1 V1 equal to A2 V2, means V is inversely proportional to E. Means as the area of cross section decreases, velocity of flow will increase. So like you are given water to the trees with using a pipe. If you hold the mouth of the pipe, press it too much, then water will go at the large distance, means its velocity will increase because you are decreasing the area. So that's why velocity increases. So this V is proportional to 1 by A, means they are actually inversely proportional to each other. Area of cross section decreases, means flow velocity will increase. Okay. Now, this equation that I have written here is called equation of continuity. Equation of continuity. Is it coming from any fundamental law, or it is just valid only for this fluid, or is it coming from any fundamental law? Which fundamental law? Conservation of mass. It is coming from the conservation of mass actually. Why? See the first line. You consider that the volume of the fluid going in equal to the volume of the fluid coming out. Same fluid is flowing. Consider the density of the fluid to be rho. Multiply both sides. So that is the mass of the fluid that enters the pipe in time delta T will be equal to mass of the fluid that leaves the pipe in time delta T. So conservation of mass is utilized here. In a certain amount of time, the mass will go in. The same amount, in same time, same amount of mass must go out, because there is no leakage such that I can extract the mass in between, or I can inject the mass in between. So that is that equation of continuity is not a new law. It is directly coming from the conservation of mass in case of fluid motion. Okay. Now, if conservation of mass is applied here, then other conservation law can be applied here, that is conservation of energy, and that is called Bernoulli's principle in fluid mechanics. So equation of continuity and Bernoulli's principle, they are not the particular law of the fluid mechanics. These are actually the consequences of the basic conservation laws, like conservation of mass and conservation of energy. See, we will not prove the Bernoulli's theorem, we will just demonstrate the Bernoulli's theorem, what it says. that the fluid entering the pipe with a velocity v1, fluid leaving this pipe at this end with velocity v2. I consider some reference level. You can consider it as if it's a ground. The height of this point is considered as h1 above the ground. Height of this point is considered as h2 above the ground. The midpoint of this cylindrical sections is considered as a height h1 and h2 at these two ends. And we consider that the pressure near this open end is P1 and pressure at this end is P2. Okay. And fluid inside the pipe is moving in a streamline and it's a Newtonian fluid. Then, what Bernoulli's principle says? It says that calculate the total energy for this position at point 1, calculate the total energy at point 2, total energy. How many types of energy this fluid has? How many types of energies it has? See, fluid is moving, so it has kinetic energy. Fluid is changing altitude in the pipe, so it has potential energy. Is there any other form of mechanical energy? Apart from this kinetic and potential, is there any other form of energy? See, what are the form of mechanical energy? Kinetic energy and how other form of energy will come as a mechanical energy? Kinetic and potentials are already considered as mechanical energy. Then how other form of energy will come? Many of you are eager to say pressure energy. That's why I asked this question. That there are only two forms of the mechanical energy we know. One is kinetic, another is potential. Then we should remove the pressure energy and rewrite the Bernoulli's theorem. Then it will be our new theorem. That is the mechanical work done, which is termed as the pressure energy. Because mechanical work equal to difference of the mechanical energy at 2 points. That is the work done. This work is done by mechanical forces. So this mechanical work done means difference of pressure energy. That's why it is termed as pressure energy. It does not mean there are 3 different forms of the mechanical energy, that is kinetic, potential and pressure energy. It is the 2 form, and that is the work done by the mechanical forces. That is the work done by pressure. Pressure is creating some force. That's why it is producing some work done, and that is considered as the pressure energy. Now, we know the form of kinetic energy, half mv square, potential energy, mgh. What about the pressure energy? What about the form of pressure energy? Is it pressure itself? Pressure into volume is equal to work done. You read in thermodynamics. pressure into change in volume, that is the work done, that is considered as the pressure energy. So what is pressure? Energy per unit volume. That's why it is termed as the energy density. Pressure is also termed as energy density, means energy per unit volume, because pressure into volume will be work done. So work done by volume will be pressure. Work done is similar to energy. So energy by volume means, anything by volume means density. Mass by volume means mass density. So work done by volume, that is energy by volume, means energy density. That's why we call pressure itself is the energy density. Okay. Now, then we can write at this point, kinetic energy is half m1 v1 square, half m v1 square. At this point, half m v2 square. But m is not a very suitable quantity to discuss this motion of the fluid. So which one we should use? Density. Instead of mass, we should use density. So I will divide mass of the fluid by its volume to write density. Then the formula half mv square if is kinetic energy. We want to calculate the kinetic energy per unit volume. So divide half mv square by volume. It will be mass by volume, that is density. So kinetic energy density at this point will be half rho v1 square. Similarly, potential energy density will be rho g h1, rho g h1, because mgh divided by volume, m by volume will be density, that is rho. So this is kinetic energy per unit volume. This is potential energy per unit volume. And E1, that is pressure energy per unit volume, that is itself pressure. Pressure energy per unit volume, that is pressure itself. So this is the total energy per mechanical energy per unit volume at point 1. According to Bernoulli's theorem, this should be equal to P2 plus half rho V2 square plus rho G H2. Means at any point, energy per unit, total mechanical energy per unit volume will remain constant. That is the conservation of energy. You can consider here at point 1 and point 2, it may happen that any form of the energy may increase, other form of energy may decrease, but the sum remain same. That is the conservation of energy for fluid motion called the Bernoulli's theorem. Okay. Now sometimes it generally, in that case, if I will write for any point P plus half rho V square plus rho GH, this sum will become constant at each point of a moving Newtonian fluid in streamline motion. In any streamline motion of a Newtonian fluid, this quantity P plus half rho V square plus rho GH will remain constant. Means total energy density remain constant. Energy density will not change. It may happen that kinetic energy will change, decrease, potential energy will increase, pressure energy will increase or decrease, but whatever be, sum must be intact. There is no change. Now sometimes you will find this Bernoulli's principle written in this format. P by rho G V square by 2G plus H equal to constant. Means you are dividing the entire equation by rho into g. Then you will get P by rho g, then V square by 2g plus h, that is equal to constant. Dividing the entire equation by rho g. Now this equation is stated like this. Same Bernoulli's principle. Bernoulli's principle initially said that energy density, total mechanical energy density at each point will remain constant. Second thought is taken as total head at any point in a moving Newtonian fluid will be constant. For a Newtonian fluid in straight line motion, sum of the total head is constant. Now what do we mean by head? HEAD, simple head. You will say that, sir, it will create headache. Too much. One form is there, okay, fine. Now you are saying that some of the heads remain constant. Centimeter rainfall. How is it measured? Why it is measured as stated in length, unit of length? Means if there is a certain rainfall, it should be measured by collecting all the rains in a container, on the water in the container, and measure its volume. Then it is that much liter. So you have to say every people, there should not be any wastage of any drop of the rain. Collect all this raindrop, come to a park, there is a large container is there, put all this raindrop that you collected in there, in that container, and measure its volume. Then I will say how much raindrop is coming. I will declare. So in this entire process, it is completely absurd process. Then how it is measured? These are called the gauge measurement. G-A-U-G-E, gauge measurement. There is an apparatus kept in the weather forecasting office that is called the rain gauge. Rain gauge. There is a specific tube, okay, that is exposed to atmosphere. Whenever there is raining, after a certain time, a certain amount of height of the liquid is developed in that cylindrical tube, and predicting that if it is 30 centimeter height, they are predicting today there is a rainfall of 30 centimeter. Means the rain is falling by that much amount that within a certain time it will fill 30 centimeter of that tube. So that's why it is termed as the rain gauge and rain gauge, or rain gauge sometimes people pronounce. This one is the gauge measurement. Similar to that, when you say the atmospheric pressure is 76 centimeter of mercury, it means that a mercury column of 76 centimeter height can produce the same pressure as that created by the atmospheric air. It is not that you have to take a air column of length 76 centimeter and say, oh, how much pressure it is giving. No. You have to take the mercury in a cylindrical tube. Its column should be of length 76 centimeter. Then it will create certain pressure at the bottom, measure that pressure, and it is equivalent to the atmospheric pressure. That's why it is termed as, normally not given in Pascal, 1.015 into 10 to the power 5 Pascal we generally not say. We say it is 76 centimeter of mercury column. So see, 76 centimeter. So pressure is measured in terms of length. So that's why called the gauge measurement. Same thing is there. Check. P by rho g. What will be its dimension? Dimension of length. P equal to rho g h divided by rho g will be a dimension of length. So that is called the pressure gauge. It is generally termed as pressure head. Pressure head. Okay. Similarly, this one, V square by 2g, its dimension is also length. You know the formula, V square equal to 2gh. Then V square by 2g in terms of length. So that is called the velocity gauge or velocity head. Okay. This one is gravitational head, because gravitational potential energy is mgh. Then divided by mg, it will give you h. That is gravitational potential energy head. So Bernoulli's theorem can be specified in this format also, where pressure head plus velocity head plus gravitational head, that is sum of the total head, remain constant. All these quantities, instead of mass density, pressure density, kinetic energy density, potential energy density, in terms of, without terms of density, it is considered in terms of height. This is called pressure head, means pressure gauge. That is height for measuring pressure, height for measuring velocity, height for measuring gravitation. Okay, so pressure head, kinetic energy head, gravitational head, sum of the all heads remain constant. That is also Bernoulli's principle. So because sometimes this form is given and student gets confused that sum of the total heads, what is head? Nothing. Just multiply with gh, rho into g throughout. It will be converted into energy density. Okay. So if you are not comfortable with this head calculation, directly multiply with rho g entire term. It will be converted to this equation and then apply. Suppose there is a room and top ceiling of the room is made with tin and asbestos, not solid structure, tin rooftop. Now suppose there is a cyclone, too much cyclone is occurring, and you put all the windows and doors closed. First of all, to save the room completely, what should be done? Should you close all the room, all the windows and doors, or you should have to open all? Open. You have to keep it open during the cyclone. Now, if you close all these things and suppose the roof is blown with the cyclone, can it fall inside the room or will it fall outside? It will break and fall inside the room or it will go outside. Why? Why it is not falling inside the room? Air is moving outside with a high velocity. So should not it be like that? It will exert very high force on the asbestos, and asbestos will break and fall on your head. If I say that it is outside during the cyclone, air is flowing with a very high velocity, so it will exert more force on the roof and roof will break and fall inside the room. Is it true? It is going there. Why? See, this only Bernoulli's principle can explain this one. Suppose this is the room all the doors and all these things are shut properly, and I consider this one is the asbestos at the top. Now, what is the situation inside the room? Is considered as, I consider a point inside the room. Inside the room, just below this tin shade, there is a point. So it is considered as point 1. Just outside this, we consider a point 2. Then from the ground, what is the height of point 1 and 2? Almost same, because tin shade is this much, very thin. So just above this tin shade and below this tin shade, the potential energy density will remain same. So write Bernoulli's theorem for these 2 points. First one, it will give you P1 plus half rho V1 square plus rho G H1 equal to, okay, then P2 plus half rho V2 square plus rho G H2, right? Now H1 and H2 are almost of same height. Suppose this is a tin shade. This point is 1, this point is 2. Is there too much difference of height? No. So rho G1 and rho GH2 will become same. So I will write both as H. So it will cancel. Now V1 and V2. V1 means velocity of air inside the room. You shut all the windows and all the doors. So air inside the room is not having high velocity. So it will produce very low velocity. Low velocity means low kinetic energy density. But outside the room, air is rushing with a very high velocity. So I can write here that V2 is much greater than V1. V2 will be much greater than V1. Then you can write P1 by minus P2, that is equal to half rho V2 square minus V1 square. So which is larger? V2, very high, because inside the room your air is almost static because you close all the openings. That's why inside the room air is almost static. So even if it has a velocity that is very low, and outside due to cyclone air is moving with a very high velocity, so they possess huge kinetic energy. And what happens in that case? P1 should be very larger than P2. This square is there. V2 is very greater than V1. So V2 square is much more greater than V1 square. So difference of this will create huge pressure difference. So inside the room pressure is very large compared to the pressure outside. That's why we are saying that moving air is exerting low pressure and static air is exerting high pressure. So pressure is high here and pressure is low at this point. Pressure into area will give you force. So on which direction force is more? And here this much. So resultant force acts in which direction? Upward, because F1 P is more and area of cross section is almost same. So P into F1 will give you force, and here P into area will give you force. So here area is A, so it is P1 into A, and here it is P2 into A. So which is more? F1. So from the bottom to the outside direction there is huge force, and as a result the shade will blow out. It will not fall inside. Okay. Because if the from outside pressure is more, then force will be directed downward, then it will fall inside the room. But here the pressure is more inside, so it will create more force on the roof from the inside portion. As a result, the roof will move up. It will never fall. But if you open all the windows and all the doors, in that case, air almost in the inside the room is not static. It has almost the same velocity as that of the outside. So in that case, pressure is same on both sides, and this force is cancelled on the roof. Because if the pressure is same on both sides, then it will exert same force from both sides. So resultant force on the roof will be 0 and it will not break. That is the mechanism. But now you say if during the cyclone all the windows are open, then all the things in the room will be going here and there. Okay. So when it is announced that a through train is passing, will be passing from platform number suppose 2, people should keep the safe distance. Passenger keep the safe distance. Why? Because through train means if we consider a very high velocity train is passing and you are just here, what will happen? It is going like this. So air between your body and the train is moving with the train with a very high velocity. High velocity means kinetic energy is very high. So which energy will be low? Pressure energy. So it is low pressure in this region. And back side of your body, that air is not moving with that much velocity. So it will create more pressure. So force will be directed. That means your body will move towards the train. And if you fall on the train, then the other part, that is the property of a fluid, property of a liquid basically, that is called the surface tension. Surface tension. Now what does it mean? Every free surface of a liquid behaves like a stretched membrane. Free surface of a liquid behaves like a stretched membrane. Okay. Like rubber membrane, if you put some weight at any portion of the rubber membrane, it will look like this. Then due to this elastic property, rubber membrane will try to produce some tension force along this direction tangentially, and due to this force, it will try to actually balance this weight of this mass. So these two forces have a component in this direction. Suppose these angles are theta, then 2f cos theta will be there, and if its mass is m, then its weight will be mg, and rubber membrane will try to balance this mass such that it will remain there and it will not go further downward. So rubber membrane on stretching will apply a force such that it can regain its shape. This is like elastic force, and this force has a component in the upward direction, f cos theta, so 2f cos theta will come and this will balance mg. The same situation happens for a free surface of a liquid exposed to air. Okay, because if you gently place a small needle here, the free surface of the liquid exactly dipped near the needle, and now it is passing like this and it will float. But if you put the needle not gently, directly, it will sink. So this position has certain similarity with the free surface of any liquid, has similarity with this stretched rubber membrane. Both will try to contract its surface area, because in this case, if you put some mass on the rubber membrane, due to stretching, its surface area will increase. Then due to, by applying this force, this rubber membrane is actually trying to go back to its original surface area. Means the rubber membrane, has a stretched rubber membrane, has a tendency to decrease its surface area. Free surface of the liquid has that same property. So write down, free surface of a liquid always tries to free surface of a liquid always tries to minimize its surface area. Minimize its surface area. So for that it will produce some force. That is the origin of surface tension force. Surface tension force is due to this origin, this cause. Now how surface tension is measured? It is measured by this force per unit length of the surface area. Surface tension S is measured by this force per unit length, or sometimes it is written as surface tension T, suppose. T equal to this force per unit length. Force per unit length of the free surface area is called the surface tension. Okay. Now, due to this, actually area is increasing. So let us consider the free surface area of a liquid is increasing by an amount A due to this stretching. Suppose initially this one, now it is increased by this much. Suppose the free surface is this one, now due to stretching its area is increased by this amount A. Then we can also write that this displacement along this direction is suppose x, and the entire surface area of the liquid is stretched here by an amount x, such that new area formed will be A. Then you can also write this one as F into x by L into x, where L is this length. Okay. Then F into x will give you, F is the force of surface tension along this direction. So F into x will give you work done. So that is W. L into x will give you new area formed. Check, this is L, so this is L, this is moved by x. So new area formed is a rectangle, it has the area L into x. So this is A. Now where this work done will store? It will be stored as energy in the extended surface, that is called the surface energy. So you can also write this surface tension as surface energy by area. Means surface energy per unit area. That is also an expression for surface tension. Now liquid has always tendency to minimize the surface area, means in that case surface energy will be minimum. So that's why to achieve minimum surface energy, liquid has this property. Clear? It will always try to minimize the surface area, because in that case surface energy will be minimum, and any configuration it always tries to minimize its potential energy. This surface energy is actually the potential energy. So you know that any system will try to be in the state of minimum potential energy, because that is called the stable equilibrium configuration for the system. Minimum potential energy configuration. Now, experimentally we can visualize surface tension. How? Can we visualize surface tension experimentally? Which experiment? That it minimizes the area. See, suppose I have a metallic ring, circular ring. And there is a hook at any portion of this ring, and with it rod is connected. Okay. And with this rod, the metallic ring is actually like this, and rod is like this. So with this rod, I can insert this metallic ring inside some liquid. And I consider also that there is a small thread. It is connected with this rod. I insert both the thread, and the thread is in this closed thread, and it is also connected to this rod. This entire thing is dipped into a soap solution. Soap solution. Okay. Immerse. Now, after soap solution, you will draw inserting it into the soap solution. Now you put entire thing out in there. You will find that two soap films will form. Soap film, like in the park or in some gathering, you will see that something is there is a soap solution is there, and there is a circle, and through that they are blowing, and as a result soap film are forming inside the air. The same thing. It is forming. So how many film will form? Two film will form. One is formed in this region between metal and thread. First soap film will form. Second one will form here inside the thread. Two different soap film will be formed. Now the thread will be in this situation, completely in haphazard way. It is not a regular shape. Now you have to do one thing. By taking a small needle, you have to rupture one of the soap film. Which one? This one. Inside. Just taking a small needle, this soap film bubble will rupture. And what you will see? You will see immediately that this thread will become circle. This thread will not be in this shape, it is completely converted in a circle. Why? That proves that surface tension minimizes the area. Why? You are rupturing which soap film? The film that is inside the thread. On rupturing this one, immediately you will find that this entire shape of the thread will not be in this irregular fashion, it will be a perfect circle. Now see, after rupturing the second film, where is the first film? Between ring and thread. Can it change can a soap film by applying a force change the shape of the metallic ring? No. But it can change the structure of the thread. Small thread it can change. Now what will happen? Why it will change the thread? There is certain area of this soap film, first soap film, but it has the tendency to minimize the surface area. Then to minimize the surface area, it has to maximize the area inside the thread. When the inside the thread area will be maximum, when its shape will be circle, because the length of the thread is constant, it is not changing. So for a given length, which figure encloses maximum area? Circle. So when the area of the circle will be, it is a circle, its area will be maximum. So this first soap film's area will be minimum. Then previously why it is not occurring? Because previously in this direction there is a surface tension force, in this direction there is also a surface tension force, and both surface tension force is actually balancing each other. So what is the net force on the thread? Zero. So thread will remain in this irregular shape when both soap films are present. Now when you rupture the second film, then suddenly this force is vanished. So in which direction force is there? Only outside, and as a result it will occupy the maximum area, and from all sides the same force is coming, so it is taking a regular shape of a circle. And once its area will be maximum, means the area of the first soap film will be minimum. So that's why the free surface of a liquid is always try to minimize its surface area. That is the experimental proof of surface tension. In any book, if you find any textbook, you will find first this experiment on surface tension. Okay, which one? Okay. Now, after this, there are certain things in the surface tension that we will discuss. One is the angle of contact. Angle of contact, this comes with this concept that if there is a surface of a solid and some liquid is dropped on this surface, which type of shape the liquid drop will take with this surface, that depends on the angle of contact. If it is like this, if it is like this, or it can be like this. This. Both. Now first case. In this case it is so here it is forming an angle theta, here it is forming an angle theta. Now for this one, what is the angle? Acute. And for that one, what is the value of the angle? Obtuse. Obtuse angle means this liquid cannot wet this solid surface. And acute angle means it has the stickiness with that solid surface, so solid will get wet with this liquid. Now why this happens? Suppose we have a glass rod, solid glass rod, and there is some water in a container, and we immerse this glass rod in this water. Then what will happen? You will find this kind of a shape at the contact point of water and glass. Little bit water is little bit moving up around the glass over the glass surface. Now why it occurs? There are two types of attractive forces we will discuss here. That is the force between the molecules. Molecules of the same material will attract each other by a force that is called the cohesive force. Cohesive force. Molecules of the different material will also attract each other by a force that is called adhesive force. In this case, water molecule will attract the other water molecule by a cohesive force, and glass molecule will attract the water molecule with adhesive force. And in this case, this adhesive force is greater than the cohesive force. So, whenever you insert a glass surface, glass object inside water, the glass water adhesive force is greater than water cohesive force. So in which direction the water molecule will feel the resultant force? Towards the glass. So it has a tendency to move over the glass surface. So that's why at the junction it is moving over the glass surface, means it will try to stick, water molecule will try to stick over the glass surface. Okay, so that's why whenever we immerse water in immerse glass inside water, it will get wet. Clear? Then draw this one. Then this is the angle of contact. This angle. Inside the water surface, the angle with this force, direction of the resultant force. Immersed portion in water makes an angle, acute angle with this, and it is theta c, called the angle of contact. Theta c less than 90 means acute angle of contact. So this adhesive force is greater than cohesive force. Okay. Again. Okay. So when you insert this one, so this is the direction of the net force, because adhesive force is more. Then immersed portion of the solid and the direction of the force, angle between them is considered as the angle of contact. Water molecules means same molecules. Water molecules and other water molecules, they are same. There is an attraction between them. That is called cohesive force. Water molecule, glass molecule, different molecule, attraction between them is called adhesive force. So water cohesive force is less than water glass adhesive force. So water will be attracted towards the glass more than the other water particles. So that's why it has this stickiness with glass.
Can it be any other material other than glass?
Yes?
Can it be any other material?
In any other material on which water will feel stickiness more. Suppose metallic, why you wash all this object by using water, all plates and all these things, because water has a stickiness towards the, water has attraction towards this materials. As a result, you can use this one for wash. Suppose you are supplied some food over lotus leaf. Lotus leaf. Lotus. Food is, you are given food on lotus leaf, dal, etc. All these things. And you are said to wash this lotus leaf by using water. It's not possible. Because lotus leaf and all these things, you will see that its surface is very smooth, and whenever water will fall on this, it is just like a pearl and move. So you cannot wash this one using water. So water will form an angle of contact, obtuse angle. So water cannot wet those substances, those surfaces. That's why you cannot wash a lotus leaf by using water. Okay, now if you immerse instead this glass rod into a mercury, glass rod is immersed into mercury, then mercury molecule has no stickiness with the glass surface. It will form obtuse angle of contact with the glass surface, because you will see that near the junction it is not moving up, it is rather moving down. Why moving down? Because mercury cohesive force is greater than mercury glass adhesive force. So mercury will try to move away from glass. So that's why the line of this force makes an angle theta. Now this theta C is angle of contact, and it is this one, not up to this. From the solid surface up to this angle is the angle of contact. Now this angle of contact is obtuse. So the mercury will not stick on the glass surface. Mercury will not stick on the glass surface. If it is acute, then the liquid will stick on the solid surface. This one is the liquid and this one is the solid surface. So angle of contact means this force is directed along this. So that's why it will move. So if you put water, certain amount of water here on this surface, what will happen to water? Will it be a pond-like structure or it will move? It will move means the net force is along this direction. So its component, one component is along the surface, so that's why the water will not stay here, it will float. But if you put a drop of mercury on a surface, will it flat? It will stay like pond. So mercury molecule will attract each other more. So it will not spread over the surface. But water molecule will not attract that much over this glass surface. Whenever water is droplet is falling on a lotus leaf or anything, then it will have this tendency, because lotus leaf molecule and water molecule has not that much of attraction. So water molecule will try to be confined in a spherical shape. So this is the angle of contact. Now we will discuss another part, that is capillary rise. At capillary rise we will is related to this calculation of the angle of contact. What do we mean by capillary tube? It is just like a straw for eating cold drinks or like this. That is called a capillary tube. Whenever you will immerse a capillary tube into some liquid, the liquid has a tendency to, suppose water, a glass fed capillary tube, suppose we are taking, then it will immerse in water, and as a result water will move inside the capillary tube due to surface tension force, because glass water adhesive force is more than the water cohesive force. So glass will attract water through it, and as a result water will rise inside the capillary tube. Now if you immerse this capillary tube into mercury, it will not rise, it will dip down. Okay. Okay. Then how much mass is rising through these capillary pipe? First we will calculate the volume of this height of liquid. What is the height of liquid? H. What is the area of cross section? Pi r square. So volume of the liquid rising through this pipe is pi r square into H. That is the volume of a cylinder. So pi r square H. That is the volume of liquid inside this capillary pipe. Now consider density of the liquid is rho. So this is the mass of the liquid that is rising through this capillary pipe. Then if you multiply with G, then you are getting weight of this much liquid inside, which rising through the pipe. Now this has this much of weight. So due to this has a tendency to fall down. Then there should be an equal amount of force on this liquid in the upward direction to hold it inside the pipe such that it will not fall due to this weight. It is rising from the horizontal level, means some force is there, otherwise due to this weight this water will fall. Then which exerts this force on the upward direction equal to its weight? Surface tension. Surface tension applies this force on this part of the liquid such that it is moving up. Okay, so you will write the surface tension force here, which will be equal to this weight. So now how to calculate this surface tension? Let us consider surface tension force is T. Surface tension force is F. Let us consider. So this force is along this direction. Surface tension force is along this direction because it is the contact surface with this liquid, and this force will be like this. Then we can consider this angle as the angle of contact. Angle of contact, write it as theta c. Angle of contact. Then can I write this force divided into two components? One is along this direction, F sin theta c. Another is along this direction, that is F cos theta c. is the force in the upward direction, which is responsible for actually pulling this water column inside the tube in the upward direction. It will actually pull. Clear? Now, is this force only at this point or throughout the boundary of the capillary tube? Capillary tube is like this. So there is boundary with the glass, there is boundary of the glass, there is boundary of the glass, all these things, and this is the liquid column formed inside, which has this almost like a hemispherical bulging form. So the force is acting like this, force is acting like this, like this, like this, like this, and their component in the vertical direction all are F cos theta into C. So this F cos theta is into C is not a single force, it is actually a sum of all such forces. So can I write that this is actually summation of F cos theta C? Summation of F cos theta C. Because if you are considering this kind of a bulging inside the pipe, then there is contact, this point is contact, 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 all this. Okay. Now this entire surface tension force, what we have written from the definition of surface tension, that it is force per unit length. Then surface tension into length will give you the force. Then if I consider the surface tension to be T, surface tension to be T, then what will be that length? 2 pi r, because this force is at every point of contact, this force occurs. So what will be the total length of the point of contacts where this force acts? The entire length in which water is in contact with the pipe. What is that length? Length of circumference of the inner portion of the pipe, that is 2 pi r. So T into 2 pi r cos theta will be, theta C will be this entire surface tension force. T into 2 pi r cos theta C is this entire surface tension force. Now write this one as pi r square h rho g. Then 1 r you can cancel. Then you can write r into h equal to 2 pi t cos theta c divided by rho into g. RH equal to 2 pi t cos theta c divided by rho into g. Okay? Which one? Oh, pi should 2t cos theta c by rho g. The pi is also cancelled from both sides, so it will become 2t cos theta c by rho g. Now suppose you are taking a capillary tube made with glass and the liquid taken is water. Then this surface tension is constant because liquid and the solid surface is specified. This is constant. Angle of contact will be constant. Rho will be constant. G will be constant. So you can write R into H will be constant. This is termed as Joule's law. R into H is constant for a capillary tube. Means if you increase the radius of the capillary tube, height of the liquid increased will be, height of the liquid in the pipe will be decreased. Radius increases means actually R, H and R are inversely proportional. So if it is thicker means it is no more a capillary. So height of the liquid will not increase that much. And as you are decreasing the radius, height of the liquid gained in through the tube will be more. Okay. Now, in this entire calculation, I have neglected something. This is an approximate calculation. I have neglected something. There is some mass of the liquid that I am not considering. This much. This much. There are certain liquid in the meniscus. This type of bulging formed is called the meniscus. When this concave meniscus is formed, some part of liquid will be there and I neglect that. By considering that liquid column is of entire height H and it's just like a cylinder. But actual liquid, amount of the liquid inside is the liquid of this cylindrical column plus liquid in the meniscus. Now meniscus calculation is not required that much. If you try to calculate the meniscus, I will show you this one. You can consider this is just like a sphere. Okay. Then what is the radius of that sphere? R. R. Radius of this sphere is R. So we can consider that this portion is a cylinder of radius R, height R. So what will be its volume? Pi R square H. H is also R. Then it will be pi R cube. If this portion is considered as a cylinder of radius R and height R, both R, then pi R square H, that will become pi R cube. So consider that cylinder, extra cylinder, that is of volume pi R cube. And from that, which portion is vacant? A hemispherical volume is vacant. What is the volume of a hemisphere? 2/3 pi R cube. So from this cylindrical volume, actually you have to subtract 2/3 pi R cube to get the volume of this 2 meniscus. This meniscus. This is shown in the diagram in 2D as if it is 2, but it is not 2 actually. It is just like a spherical and this is the cylinder. So this portion is, there is some liquid. So that is actually the meniscus. Because it is actually a spherical object, just put this spherical object like this, like this. So all these sides, there are the meniscus. So we are actually considering it is just like a cylinder and a spherical object is put here. So there is this liquid. That mass we are calculating. So that's why we consider first, this is a cylindrical portion having radius R and height R. So this cylinder has a volume pi R cube minus this hemispherical part, which does not contain the liquid, that is 2/3 pi R cube. So this is the 1/3 pi R cube, that is the volume of the liquid present in the meniscus. If you multiply this one with the density of the liquid, it will give you the weight, mass of the liquid in that meniscus, then what is the total volume? Pi r square h that you are writing. With this you have to add 1/3 pi r cube to get the full form. That is pi r square h plus this extra 1/3 pi r cube into rho g will give you the total weight actually of the liquid that rises through the capillary pipe. The weight of the liquid in the cylindrical portion plus the meniscus. That will be equal to T into 2 pi r cos theta c. That is the entire calculation. But for capillary tube, actually radius is very small, so the meniscus volume we can neglect. Volume of the meniscus we can neglect since we consider a capillary tube is of very small radius. I will ask you one question. Suppose I have a capillary tube. Its radius is given, and from the Jouling's law you know that R into H will become constant. Now for a particular capillary tube, suppose R equal to say 0.5 millimeter. Okay. And H equal to 100 millimeter. H equal to 100 millimeter. Okay. Then we consider that through this pipe the liquid will rise up to a height of 100 millimeter. Now suppose radius of the pipe is length of the pipe is given to you. Length of the initially given say 150 millimeter. Length of the pipe is given 150 millimeter. This one, length is given 150 millimeter. So what will be the situation? Check. We consider this is a length of a pipe, capillary pipe, that is 150 millimeter. From this level, radius of the pipe is given, that is 0.5 millimeter, and liquid rise up to a level of 100 millimeter, up to a height of 100 millimeter. This is the height of the water column. Clear? Now, if the tube is cut from its middle, what will happen? Now second time, before immersing, you cut half of the length and then you immerse this in the liquid. Then what will happen? Previously you have the length 150 0, 150 millimeter. You immerse this one and you find that it rises through 100 millimeter. Sorry, this one is millimeter. Now what you do? You put it outside, cut half of the length and then again immerse it. What will happen? According to Joule's law, how much it will rise? R remains same. So how much it should rise? 100 millimeter. But how much length is given for the pipe now? 75 millimeter. So what will happen to the liquid? It will overflow. It seems that it will overflow, but it will not overflow. It will not overflow. Okay. So if this type of question will come and in one option is given, it will not overflow. So that is the correct answer. It seems that it is moving up to 100 meter, so 75 millimeter is available, so it will overflow from the pipe. That will not occur. That is called a tube of insufficient length. If insufficient length is given, it seems that it will overflow, but it will not. The structure of the meniscus will be different and it will balance the weight of the liquid. It will not overflow. Have you ever seen any pipe is there and cut the pipe and put it inside? Will it come out? Suppose it is a straw of cold drinks. Immerse it and you will find that liquid rises to a certain level. Okay, through that pipe. Just after that, remove entire liquid from it, cut the straw, half, immerse it. Will you ever find that cold drinks will come outside or no? So means whatever length you will give it will adjust in that length by changing the shape of the meniscus formed at the top. So the calculation is there, but calculation is not required at all. That is for JEE. So we will only learn this concept that if there is a tube of insufficient length, still it will not overflow. Okay. So this is the fluid portion that we have completed. Next thing, and one more thing, excess pressure. There is a part of the excess pressure in surface tension. You have to remember two things. One is excess pressure, how to calculate the excess pressure. Excess pressure is calculated depending on the surface area. Now, suppose I have a water droplet. Now, if it is droplet, then this one, so how many free surface this droplet have? One free surface exposed to air or two free surface exposed to air? Only one free surface exposed to air. So number of free surfaces is 1. So excess pressure will be T by 2T by R. Excess pressure will be 2T by R. Surface tension T and radius is R. So excess pressure will become 2T by R. Just remember this formula. Don't try for the derivation of this because that is not required. And if I consider this is not a liquid drop, this is a water, this is a bubble. How much free surface area it has exposed to air? Two free surface, because inside the bubble there is air, outside the bubble there is also air. So there are two free surface exposed to air, so excess pressure will increase and excess pressure will become 40 by R. For a single exposed surface, excess pressure will be T by R. That is for a droplet, because inside the droplet there is water. So only free surface exposed to air is 1. But for a bubble, inside air, outside air. So free surface is 2. Same thing happens from the soap film. Inside air, outside air. So if there is two surfaces, surface tension will be multiplied by 2 times. So that excess pressure, some question may come directly, and if you can't identify between a bubble and a droplet, your answer will be wrong. This question comes directly. Say this type of a droplet is there and 4 options are given. So you have to write directly. Okay. So this much is for the liquid and surface tension, all these things. And tomorrow's class we will discuss the heat transfer. Heat transfer, and in part of this, some questions we will discuss. Then almost class 11's part is one brushed up. Previously we discussed the mechanics portion, now we discuss the other topics. Then in the next visit we will start with certain portions of the class 12. Okay.